Today we're going to be talking about Gibbs Free Energy under non-standard conditions. So we had previously talked about Gibbs Free Energy under standard conditions. And to remind you, our symbol for Gibbs Free Energy is delta G. And if we're talking about standard conditions, we put a little naught, a little circle up top, a little zero. So we've got delta G naught. And standard conditions mean that all gases have a pressure of 1 atmosphere. And any aqueous solutions have a concentration of 1 molar. But what if we're not working under standard conditions? How do we calculate delta G? Because we can't use all the tables we were using for using Gibbs free energies of formation. So to find delta G under non-standard conditions, so that's just delta G, no little naught on the top, it turns out that this is equal to delta G naught plus RT times the natural log of Q. So a couple things to remind you about with this equation. You've seen Q before. This is our reaction quotient. So when we were talking about equilibrium, we used the reaction quotient to predict the reaction progress, which way it would proceed in order to reach equilibrium, because it's that equilibrium constant, not necessarily at equilibrium. So the same form. And so you're going to have your products raised to whatever their exponent or their coefficients are, use that as an exponent, divided by your reactants raised to whatever their exponent is. And then R, here again, is our ideal gas constant. And since we're working with energy, we're going to use energy units. And so you have 8.314 joules per mole Kelvin, or since delta G values are typically calculated in kilojoules, it's oftentimes easier to use 8.314 times 10 to the negative third kilojoules per mole Kelvin, because that way we have the units already lined up to work with delta G. And just as a reminder, of course, we have to be using Kelvin here for our temperature, since we have units of Kelvin in our gas law value there. So that's our value for delta G. Let's see how we can calculate delta G for a reaction under non-standard conditions. So let's take a look at an example. So if I have ammonium chloride, which is a solid, and I take this, it can decompose to form ammonia gas and hydrogen chloride gas. And for this reaction, delta G is a positive 13 kilojoules per mole reaction, delta G naught. And so if you look at that under standard conditions, this reaction, because it has this positive sign for delta G here, is not thermodynamically favorable as written. And so what happens though if we change the conditions that we're under? So if this is delta G naught, then this would be at 1 atmosphere of pressure for all the gases. What happens when we decrease the pressure of those gases? If we take the pressure of the ammonia and the pressure of the hydrogen chloride, we put those down to 0.1 atmospheres. And let's say we're working at 300 Kelvin. Let's figure out what that calculation is going to come out. So just as a reminder, our equation that we're working with here is delta G naught plus RT natural log of Q. And so our delta G naught is 13 kilojoules per mole. Our value for R that we're going to be using is 8.31 times 10 to the negative third kilojoules per mole Kelvin. And then our temperature was stated at 300 degrees Celsius, which, if you look carefully here, means that we have to turn that into Kelvin. So it's 300 degrees Celsius, so it's 573 Kelvin. And then we need to take the natural log of Q. Okay, so Q is going to be products over reactants. So in this case, it's going to be the pressure of the ammonia, which is 0.10 atmospheres, times the pressure of the hydrogen chloride gas, 0.10 atmospheres, over 1. Because remember, solids don't figure into our equilibrium constant expression, so they don't come into Q either. And so if you take all these numbers and you plug them in, you'll get that this is a negative 8.9 kilojoules per mole of this reaction as written. And so now this reaction, by changing that, now this reaction becomes spontaneous as written under these new pressure conditions. And so it is really important to consider what concentrations you have in a reaction when it comes into determining whether a reaction is spontaneous or thermodynamically favorable, as AP likes to say these days, as written. So this reaction will proceed in a forward direction in order to reach equilibrium. So as useful as that equation is in terms of determining what the value for Gibbs Free Energy will be under any particular conditions, it also allows us to gain some insight into the equation itself and the relationship between Gibbs Free Energy and the equilibrium constant. So if I take a look at this, we know that at equilibrium, delta G is equal to 0 and Q is equal to K. That's part of the definition of what's going on at equilibrium. Q is equal to K. And we talked about the fact last week that delta G is equal to 0. And so if we take this and we plug these values in to our equation, so delta G is 0, delta G naught is a value based upon those standard those standard conditions, RT ln of K. So let's take this and rearrange this and solve for delta G naught. So delta G naught is equal to negative RT ln of K. What we have now is we have a relationship between the Gibbs free energy and our equilibrium constant. And so this is incredibly, incredibly powerful because if we know delta G, we know K. And if we know K, we know delta G. And it also allows us to get a little bit of further insight into what's going on because as it turns out, if you look at the way this equation works, if K is greater than 1, then you'll get a positive value for the natural log of K, and delta G naught is going to be negative. So if K is greater than 1, your value for delta G is negative. If K is less than 1, natural log of that negative value is going to give you a value for delta G that ends up being positive. And so we have a really nice connection between the value for our Gibbs free energy and our equilibrium constant. And that's going to be incredibly useful because that means that our Gibbs free energy really is a reflection of your equilibrium constant. And that's just amazingly powerful. So what can we do with this? Let's take a look at another place where we can apply this value and this information. So let's take the reaction between dinitrogen tetraoxide and that decomposition into nitrogen dioxide. And for this reaction, Kp, your equilibrium constant given in pressures, is 0.113. So if you think back to what we know from our equilibrium, then we know that at equilibrium, this reaction favors the reactants because the denominator is larger. So let's see what that translates to in terms of delta G naught. So let's see. Here we go. We know that delta G naught is equal to minus RT ln of K. Okay, so minus R, so 8.31 times 10 to the negative third kilojoules per mole Kelvin. And then we're at 2298, so 25 degrees Celsius, 298 Kelvin. And then we'll take our natural log of 0.113. And so this is 5.4 kilojoules per mole. And so this process is not thermodynamically favorable as written in that forward direction, in that the products are not going to be favored at equilibrium. So not thermodynamically favored. And so that's our products. At equilibrium are not thermodynamically favored. That positive sign for delta G tells us that our products are not thermodynamically favored at equilibrium. And that equilibrium constant of being less than 1 tells us that as well. Again, there's that connection. But what now happens if we change our conditions? So we're not under standard conditions. So now if we come in and we take a look at different pressures. And so let's take this to a pressure where the pressure of NO2 is 0.112 atmospheres, pressure of N2O4 is 0.453 atmospheres. Let's calculate delta G in this situation. And so again, the equation we're using here is delta G is equal to delta G naught plus RT ln of Q, because we are no longer at equilibrium. And we're not at under standard conditions any further. And so if we look at these, delta G naught we figured out was 5.40, I lost a zero, put that back in there, 5.40 kilojoules per mole Kelvin. And, get rid of that Kelvin, erase. Okay, kilojoules per mole. And then R is this 8.31 times 10 to the negative third kilojoules per mole Kelvin. That's where my Kelvin comes in. I've got a temperature. At that same temperature, I've got 298. And then I need to take the natural log, and I want to use Q, which again is going to be products over reactants. And so my product as written is NO2, and so I'll take 0.112 atmospheres, and I need to square that because its coefficient is 2 in that balanced chemical equation. And I'm putting that over my reactant, which is N2O4, which is 0.453. We don't need any units in there because it's going to be a unitless value. And so when I take the natural log and then do all the math behind this, I find that we have negative 3.06 kilojoules per mole. So now this reaction is going to be spontaneous under these conditions, or when I say spontaneous, again, what we mean here is our products are thermodynamically favored. Thermodynamically favored under these conditions. And remember, your textbook uses the term spontaneous. AP is using the term thermodynamically favored as being more rigorously correct and a little clearer. And so we see that we've got this relationship that the conditions that we're under, those concentrations, can change. And actually, if you look at Q, this value for Q, for the right here, this value for Q, this is 0.0329, which is less than Kp, and so we know we need to form more products in order to reach equilibrium. So again, products are thermodynamically favored at this time. Thermodynamically favored, we're moving towards equilibrium. Let's take a look at one more example where we're going to put this into use. So let's go backwards. We just used the K in order to calculate delta G naught. Now let's use delta G naught in order to calculate K. So here's a problem where I've got the decomposition of water. And so delta G for this reaction is 474.4 kilojoules per mole reaction at 25 degrees Celsius. So this reaction is not thermodynamically favored, which actually makes perfect sense if you think about it, because water doesn't normally break down into its elements at room temperature. And so it makes sense that delta G is going to be a large positive number because it's not thermodynamically favored. So now let's go in and let's calculate what our K value is going to be for this reaction. So here again, I want to relate delta G naught to K. So delta G naught is minus RT ln of K. So if I put our numbers in here, I've got 474.4 kilojoules per mole. Negative R, once again, is at 8.31. And since my other number is in kilojoules, I'm going to use this one in kilojoules. Kilojoules per mole Kelvin. And then our temperature that we're working at is 298 Kelvin. And natural log of K, which is what I'm going to be solving for. So in order to take this equation and solve for it, I will divide 474.4 kilojoules per mole by negative 8.31 times 10 to the negative third, and by 298 Kelvin. That'll give me the natural log of K. And just as a reminder, I'll write that out here. Once you have that value, if you need to solve for something what you've taken the natural log of, then what you need to do is you need to take both sides and raise it e to that power. And so I'll take both sides of this equation, e to that power. And when I do that, I get the value of k as 6.34 times 10 to the negative 84th. That's an incredibly, incredibly tiny number. And so for this reaction, my reactants are favored, which makes perfect sense. It is not thermodynamically favored as written, not thermodynamically favored to form the products. And if you were to look at this in a graph form, let's switch up colors for that. If you look at this in graph form, if I were to look at a reaction coordinate diagram where I've got my Gibbs energy on the y-axis, this is a huge change in energy from my reactants to my products. And so you see all of those pieces coming together with that relationship between delta G and the equilibrium constant. That is so incredibly useful for us. And it's very helpful.